Now that we have learned about all of the different simple machines, now let's talk about how we can use those machines. There's a couple of different things that we can calculate as we use them. We can calculate the efficiency of a machine as well as the power of that machine. Today we'll focus on efficiency. So what is efficiency? Efficiency is a measurement of how completely work input is converted to work output. So here is your equation for efficiency. It is equal to the work output divided by the work input times 100%. Okay, so the work output, this is the work of the machine. So you may have to calculate that using the equations that we've used before for work. Divided by the work input, this is the work that the human does. So you may have to calculate that in a problem before you can calculate the efficiency. Okay, so work out divided by work in times 100. Your unit for your efficiency calculation is a percent sign. So efficiency is a percent of how well the machine does at converting that work. Now, 100% would be wonderful. In an ideal world, it would be 100%, but no machine is ever exactly 100% because we always lose some to what? What do we always lose some of our work to? Hopefully you guys said friction. That should be becoming a pattern now. Friction. We always lose a little bit because of friction. So it'll always be a little bit less than 100%. A very efficient machine will be in the 90s. A decent machine will be in the 80s. Anything less than 80 is considered not very efficient. So let's try a practice problem. A worker exerts a force of 500 newtons to push a 1500 newton sofa 4 meters along a ramp that is 1 meter high. What is the ramp's efficiency? All right, we have a lot of numbers in this problem, so let's see what we have here. So we have a ramp. We have a sofa that we're pushing up it. Okay. The worker has to exert 500 newtons of force, so that's the human. And the sofa is 1500 newtons, so that's the machine's work. And we've got to go 4 meters for a height of 1 meter. Okay, so there's a nice picture diagram of what we're doing to sort of give us a visual representation. Okay, so what kind of information do we know? We know our effort force, that's the human, is 500. We know the effort distance, so the human's different, distance is 4. We know the resistance force is 1500 because that's the force of the couch. And we know the resistance distance is 1 meter because that is the height of the ramp. Okay, so we are putting together all this stuff that we've been building over the last several days. Okay, so first I need to calculate work input. So remember that work is equal to force times distance. We need, for the input, we need the force and distance of the human. We need the effort. So our effort force is 500. Our effort distance is 4. So we do 500 times 4 is 2000 joules. Remember, work's unit is always joules. Then we need to calculate our work output. That's the work the machine does. So for that, we need the resistance force times the resistance distance. So we do 1500 times 1. That is equal to 1500 joules. Okay, and then we use this equation right up here in the corner. So we do the work out divided by the work in. So we're going to do 1500 divided by 2000, and then we're going to multiply it by 100. Okay, so 1500 divided by 2000 times 100. So our final answer is going to be 75%. 75%. Okay, percent sign is our unit there, always for efficiency. Okay, if you don't know how I got this, please get into contact with me, because this is a big one, because we had to, do 3 different equations basically. We had to do the work equation twice, then the efficiency equation. So we're putting all of our skills together that we've been building within this unit. So if you need some help, please get into contact with me so that I can help you out, because up next is your independent work on efficiency.